This is the video for Math 120, section 2.7. I want to remind you of the equation of the line. We're going to need that for the equation of the tangent line. We also need the definition of the derivative. The derivative is the slope of the tangent line to the curve. There are two limit definitions of the derivative as a function that we're picking up here. So this is the derivative as a function. And you'll need to have them memorized and be able to use to calculate the derivative. So f prime of x, this was f prime of a when we were looking at derivative at a point. So the a's in here become x's also. This is f prime of x, and instead of x goes to a, we'll have a goes to x here. So study the four definitions enough so that you're clear about which goes where and when I'm asking for which. When I ask to find the derivative and I don't give you any information, then you're finding the derivative as a function. Just a reminder that the derivatives won't exist at heavy oscillation, jumps, vertical asymptotes, holes, and cusp of corners. For the first problem, we're just running through this example with 2x cubed minus 5x as our f of x with one of the definitions of the derivative. So we've done several of these before, and I'll give you some more in some notes. We went over the graphs of the sketching of a derivative. So if we start with the function f here, and then we want to sketch the derivative, everywhere we have a maximum or minimum will be a 0 on the derivative graph. Anywhere the graph is going down on the original graph, the derivative will be below the x-axis. Anywhere the graph is going up, increasing, the derivative will be graphed above the x-axis. There will be a max or min on the derivative where there's an inflection point on the graph. So they're going to be asking you about pieces of this. You just go down one at a time thinking about what each of these pieces actually mean. So we have max and min on the original function, and then we have a prime, b prime, and c prime that go with a, b, and c points that map to the derivative function. For the next problem, we have four graphs, but first they say these are the four derivatives that are given. So these are our derivatives graphs, and we want to know which graphs these came from. Of course, we've looked at these already, looking the other direction. So my derivative should be below the x-axis, should be above the x-axis, should be below. This one should look like a parabola upside down, below the x. So it should go up, hit 0, then come up and hit its high point and come back down, hit 0, and then go down again. So I can see this one matches with number 3. These are all lines, so I should have lines for derivatives too. But I cannot have a derivative at a corner. And this is a corner. Can't have derivatives at corners, so there should be some jumps at corners. For the next one, we have the absolute value of x minus 8. So for x bigger than 8, we actually are looking at the positive piece here. So we could just drop the absolute values, and that's what they're asking for here. And if x is smaller than 8, we would be looking at the negative piece, and we'd have to put negative on x minus 8, drop the absolute values, and change the signs. So the function that we get in this box would be just x minus 8. And we're going to use that function through this whole exercise down to here for x is less than 8, because they want us to do for x greater than 8. So this is the function for x greater than 8. So we'll put in x plus h minus 8 would just be drop the absolute value x plus h minus 8. For the second piece, if x is less than 8, we have the negative of the absolute value here. So I need to put in the negative of x minus 8. Now I could just put negative x plus 8 here, and that would be fine too. So chosen small enough so that this is less than 0. And so x plus h minus 8 equals, therefore. So the absolute value here, since this is less than 0, will be the negative of it. So we throw a negative all the way through the parentheses here. So for this problem, this is x plus h minus 8, and then we're going to be subtracting off this one. We do the same steps we've done in previous ones. You've had several of these to do on a worksheet too, so make sure you're looking at that. For this graph, we're looking at zeros at the maxes and mins. It looks like it's flattening out. It's going negative, so this part will be graphed below, but it's going negative. Notice there's an inflection in here. There's an inflection right in here. So it's going to hit a low point or a high point. Since this is going negative, it'll be a low point. Since it's going positive, this will be a high point. And then over here, since this is going negative, this will also be a low point. So we're looking for a graph that has two zeros. It's got a high point on the y-axis, and it should hug the x-axis at both ends. High point, this has a low point on the x-axis. This has a 0, and this has a 0 on the x-axis. So we've eliminated everything but the correct answer. For the next graph, I can see I'm going to have three zeros. I have a minimum, a maximum, and a minimum. So I have three zeros where the tangent's going to lay flat. The tangent will be straight across there, laying flat. Horizontal tangents, three zeros. So already I can tell that this one cannot be an answer. This one can. Not sure if it is, but this one could be the answer. This graph has both a vertical asymptote and a horizontal asymptote. I can see it's coming up very sharply, and it's flattening out, very flat, along the x-axis, hugging the x-axis. So I can see we have 1, 0. We have an inflection in here. So we're going to have either a high point or a low point. It's increasing here, so that means the derivative is positive, which means it will be above the x-axis. So both of these could be our derivative. They're both above the x-axis. There's a 0 on the origin. Both of these have a 0 on the origin. This one now is going down, so that means that it's below the x-axis, so this one could not be our graph. This one has a point of inflection here, so it's going to come back up. So this is going down, but then it's supposed to come back up and hug the x-axis. So this could not be the graph either. So I've just explained how you can find the actual graph. If you have a corner or a cusp like this, you will always have a jump, because this slope is coming in negative, so everything I graph for the slope here will be below the x-axis. This slope is going positive, so everything will be above. This could be the graph of my derivative. There's more curves going on here, so there might be a better solution presented. This could not be the graph of my derivative. The derivative would have to be negative before 0, and this is above the x-axis, so it's positive before 0. Note that this is coming in vertically here. It's not just a corner, so there's not an actual jump. Well, there is a jump, but there's not a small jump here. There's a vertical asymptote here, so there would be an infinite jump. This one also has a vertical asymptote, so there's going to be a vertical asymptote in the derivative. Notice that the derivative is all positive here, and it's all positive here. Positive on the derivative, on the slope, means that it's being graphed above the x-axis. This one's below the x-axis. This one's above. This side looks good. This side does not. So positive slope means everything is going to be above the x-axis. It looks like it's flattening out, so I should see it hugging the x-axis here. It's flattening out, hugging the x-axis there. Here they're asking you to find the derivative, and it's using the definition of the derivative. So you just want to state what the derivative here is. The domain here, this is a nice function. It's just a line, so the domain's going to be all reals. And we take the derivative, we end up with something else that's a line, so the domains will be all reals there too. So if it's nice, you're going to have all reals. Down here, nice function, all reals. That's just a line. For number 12, again, we have a nice function, domains just fine. You want to use the limit definition of the derivative to find this, f prime of x, f prime of t in this case. Note that you're going to have to use t as your variable. If you don't put t's in, you put x accidentally, it's going to fuss at you, give you those little red x's, and you'll just have to know that you should put an x. This one is going to involve the conjugate trick, and the domain will be just about the same as the range, as the domain for its derivative rather, but the derivative is going to end up with the square root in the bottom, so you won't be able to include what makes this 0. Note that your variable is u here, so when you find the derivative here, you're going to end up with a statement involving u. It does not say to simplify the derivative. Not differentiable means you can't have a derivative there, and there are 6 places where things are not differentiable. Holes, heavy oscillation, vertical asymptotes, jumps, corners, and cusp. So 6 different ones that you're looking for. So any place where you have any of those, and there's only 2 of them on this graph, a smaller x and a larger x. Same is true down here. Corners, cusp, vertical asymptotes are places where it is not differentiable. So they're looking for the x value where it's not differentiable. For the next graph, we want to identify for each curve if there's a derivative available. So I'll try maybe looking at a here. If I took the derivative of a, it has a high point somewhere in here. So its derivative should have a 0 somewhere in here, and b does. It has an inflection point in here, so its derivative should have a high point, and b does. It flattens out, it flattens out. So it looks like a would be my function. So a is the function I'm looking for. So if a is my original function, then the derivative of where b would be its derivative, then b, looking at the derivative of b, I'm going to check it and make sure, because it could be that there's another one in here that is a better choice for my function. But b has a high point, so there's a 0 at c. That looks good. It's flattening out. The end behavior is flattening out, and that's true for c. The inflection points, there's 2 inflection points, so this is going up with an inflection point, so it should have a high point on the C graph, a maximum on the C graph. This one's going down, so at the inflection point it should have a low point or a minimum on the C graph. So I'm feeling pretty good about A, B, and C being what my f prime, and f double prime are. So here it says use the delimit definition of the derivative to find f prime. Well, that's just f prime of x equals. Well, once we have that, we're going to use that and take a second derivative. So second derivative means the derivative of the derivative. This is the dy dx form of the derivative, the second derivative. So we put d squared y dx squared. Taking a derivative is not the same as taking the derivative and squaring it.